Hey everybody, welcome. This video is going to show you the proof of Theorem 2.7 and Theorem 2.8 from our textbook. Remember, math loves you. Let's go ahead and prove Theorem 2.7. First, we should say what this theorem even says. It says given f of x is equal to g of x for all x not equal to c, oops, messed up my a symbol there, in an open interval containing c. Remember, c is an element of the real numbers. So we can go a little bit to the left of c and a little bit to the right of c, and f of x is going to equal g of x in that interval. Well, this means that if the limit of g of x as x approaches c is equal to L, then the limit of f of x as x approaches c is going to equal L as well. Remember, we're saying this is true for all x not equal to c. So if f of x is equal to g of x for every x value not equal to c, except c itself, on some sort of open interval to the left and to the right of c, then the limit of g will be the limit of f. Let's go ahead and prove it. So we're going to use our epsilon delta definitions. And remember that we're given that the limit of g of x as x approaches c is L. That's the if part of our statement there. So by the epsilon delta definition, let's see what we get. We get that for all epsilon greater than 0, there's going to exist some delta greater than 0, such that the absolute value of g of x minus L is less than epsilon whenever 0 minus the absolute value of x minus c is less than this delta. So when we choose a value of x within that interval around c, we will get a value of g of x around our epsilon interval of L. Okay, so since f of x is equal to g of x everywhere but c, again on our open interval, and let's even write that interval in interval notation for everybody who likes that or has trouble with that. So c minus delta to c, parentheses, because it's not included, union c to c plus delta, all parentheses since they're not included. Okay, so since f of x is equal to g of x everywhere but c, then the absolute value of f of x minus L is less than epsilon also whenever 0 is less than the absolute value of x minus c is less than delta. And that's the definition, the epsilon delta definition of the limit. So aren't we done? I think we are. Congratulations. So this proof is really just spelling out what we already know. That's it. That is the definition of the limit as x approaches c of f of x is equal to L. So since we proved it, since we showed it very clearly step by step, we're good to go. Done and done. Box it out. Remember, we're allowed to do this because the definition says nothing about what happens at x equals c. The definition of the limit, that is. It only talks about what happens around C. Oops. Okay. So we're finished with that proof. Now let's go ahead and prove theorem 2.8, the squeeze theorem. Both of these theorems are going to be really important, and we're going to be using them for a while. The squeeze theorem states, if h of x is less than or equal to f of x is less than or equal to g of x. So if all my y values for h are less than the y values for x or less than the y values of g, for all x that are elements of an open interval containing C, except possibly C itself, right? Because there could be some sort of hole at C. And that's why we need this theorem to begin with, is if f of x is not defined at C, or if there's a hole at C, then we need to kind of squeeze it between these two other functions. Okay, and if the limit as x approaches L, the limit as x approaches C, sorry, that should be a C, of h of x is equal to L, and the limit as x approaches C of g of x is also equal to L, then the limit as x approaches C of f of x is equal to L. I'm sorry that my C looks like an L up there. It's the limit as x approaches C of h of x. Okay, so that's my whole theorem there. That's the squeeze theorem. Let's prove it. Prove it good. For all epsilon greater than 0, there exists a delta 1 greater than 0 and a delta 2 greater than 0. We're going to define two different deltas here. The same epsilon, we're choosing some sort of epsilon around our function values. We get two different deltas such that we can define these two different absolute values. So the absolute value of h of x minus L is less than epsilon whenever 0 is less than x minus c is less than delta 1. So delta 1 is kind of belonging to my h of x, let's say, in that case. And the absolute value of g of x minus L is less than epsilon whenever 0 is less than x minus c is less than delta 2. So these are simply just the epsilon delta definitions of our limits. And we were given that the limit of h of x as x approaches c is equal to the limit of g of x as x approaches c is equal to L. That's what we were given, and so we just wrote out those definitions. That's all we did. We said, well, there must exist some delta 1 and some delta 2 such that this is true. Easy. Easy peasy. Lemon squeezy. Okay. Let's see what this actually kind of looks like on a very loose, non-accurate graph. We're just sketching it out. So our y-axis and our x-axis. Let's approach this value c. That'll be the x value we're approaching. Let that be our h, our function h. I'm going to make an open circle there because the open interval might not actually include c, so except possibly c itself. All right, so that's h. Remember, we want h to be less than f, so f is going to be a little bit above it, and then we want f in between g and h. So there we go. Our values of g, our function values of g are greater than f, which is greater than h. Good. F is squeezed in between, hence the squeeze theorem's name. h of x is less than or equal to f of x is less than or equal to g of x. What? Oh yeah. All right. Let's keep going. So remember, we've got this kind of delta 1 and this delta 2 somewhere around our C, right? It doesn't really matter which one is bigger than the other one, but the delta 1 is our delta that goes along with our limit of h of x, and the delta 2 is the one that goes along with our limit of g of x, and they exist, and there's some sort of interval around C. And we chose some epsilon neighborhood there around our limit, so that's our limit. So, okay, that's L plus E plus epsilon, and here's L minus epsilon. And epsilon's the same for all these functions. It's some chosen epsilon, whatever it happens to be, however big or however infinitely small. Also, please note, there has to exist a delta 3 such that those values of h of x, which are less than the f of x, which are less than the g of x, those function values, those y values, within this delta 3, that interval of the delta 3 around C, the y values have to be in that order. The h has to be less than the f, has to be less than the g. On some interval right and left of C. So C plus delta 3, C minus delta 3. Hey, that's exactly what we were saying to begin with. This is what we were given. We were given that those function, that f of x is in the middle. Duh. If we were given that that's true, like, of course, automatically we have some sort of delta 3 that, such that this is true. I drew it right there on my graph, right? The g is bigger than the f, which is bigger than the h. The f is squeezed in between. That must be true on some delta 3 plus or minus our c. Okay. So what we're going to do, now that we define this delta 1, delta 2, delta 3, again, on my graph, it's pretty clear that the delta 2 is the smallest, but whatever functions we might have, this is all arbitrary stuff in general. The graph is just to kind of demonstrate, not to really say anything in particular. So in any case, let's choose the minimum of delta 1, delta 2, and delta 3. And we'll just call it delta. Okay, so this is going to be our delta for our final definition of this limit. And remember, what we're trying to prove here is that the limit of f of x as x approaches c is equal to L. All right, in my picture, delta 2 is the smallest, but that does not have to be the case. Again, that's just for my little picture, and really this proof is in an arbitrary situation. Arbitrary meaning it could be anything. My functions could be anything as long as h is less than f is less than g, and as long as the limit of h is equal to the limit of g is equal to L. Okay, so now that we have delta, then if 0 is less than the absolute value of x minus c is less than delta, this delta that was the smallest of our delta 1, delta 2, delta 3. In other words, if x is within our delta interval around C, we know for sure, because of the way we define delta, we define it as the smallest of delta 1, delta 2, delta 3, that the absolute value of h of x minus L has to be less than epsilon, and the absolute value of g of x minus L has to be less than epsilon. Because from our definitions, we know that when we're within our delta 1 limit, we've got our h of x minus L less than epsilon. And when we're within our delta 2 little interval, we have our g of x minus L less than epsilon. So we have it already. Look, let's look at the graph. Again, this is just my little rough sketch, but this delta 2 is the smallest. So whichever one is the smallest, when you're within that little tiny interval in there, of course the rest of the bigger intervals are going to be satisfied, right? We chose the smallest of the intervals. So if our other deltas were bigger, whatever, they're satisfied, no big deal. We chose the minimum delta interval. Of course it works for everything. For both h of x and g of x. Smiley. We're almost done, believe it or not. So we're gonna rewrite this h of x minus L and this g of x minus L. And we're gonna say the absolute value is really just saying that negative epsilon is less than h of x minus L is less than epsilon. Definition of absolute value. Let's add L to all three sides and get L minus epsilon is less than h of x. And at the same time, negative epsilon is less than g of x minus L is less than epsilon. Let's add L. So really all we care about is that g of x, really all we care about is that g of x is less than L plus epsilon. Okay, so do you see how like the one side has the L minus epsilon, the other side has the L plus epsilon? And what's in between h of x and g of x, everybody? Drum roll, please. We were given that h of x is less than or equal to f of x, which is less than or equal to g of x. The squeeze theorem, f is squeezed. And so if we put these other inequalities on the two sides, we now have that f of x is really less than L plus epsilon all the way over there, and on the left-hand side we get L minus the epsilon. So we squeeze the f inside of these inequalities, and now we can write our absolute value. Look, we get the f of x, we got the L minus epsilon, we get the L plus epsilon. Put all three together. L minus epsilon is less than f of x, is less than L plus epsilon. And remember what we're trying to prove. We're trying to prove that f of x minus L absolute value is less than epsilon. That's our definition. That'll say that our limit is actually L for f of x. So by just subtracting L from all three, we get negative epsilon is less than f of x minus L is less than epsilon. Okay, almost there. This is the definition of an absolute value. We've got this. Let's just put it into an absolute value. Woohoo! We have the absolute value of f of x minus L is less than epsilon. As desired. Because remember, up top, we already defined our delta, right? We found the delta where this is going to be true. This is desired for the definition of the limit of f of x as x approaches c is equal to L. Smiley face, box it out.